right, let me share my screen. Could you all give me a thumbs up if you could see the screen? Okay, I can't really see the thumbs up, but I take it it's shared properly. All right, so let's go through outdoor insulators and the practical a little bit. All right, there were 3 things I asked you to do based on what you had captured during the practical. Describe with images from your recordings. You must describe each phase of the pollution flashover mechanism. About 30% of people did that. You must conclude what voltage rating each of the insulators has. See table. There were a couple of tables. I'll go through that just now. About 50% attempted that. Most people used the wrong tables and the wrong thought process. And you must also determine what type of insulator performs the best under polluted conditions. Now, the insulators actually had different ratings. So it was about the type of insulator, and you needed to justify that. And I guess 50% of people justified it by looking at the silicon rubber and the hydrophobic properties. Okay, so it was a big thing that not everybody read all of that, and not everybody put the report into like a decent form. There's also meant to be a video file uploaded, but not much we can do now. All right, so let's go through the course notes. I'm assuming you've gone through the video, but essentially most of the work for the practical was in the course notes. There's some details about the different types of insulators. They are the measurement distances that you need. They were defined in the course notes. So yeah. And then the unified specific leakage distance was also defined. Right, some details about the materials. You could have taken it from here, looked at the original reference, hopefully not just copied and pasted. And then the types of insulators is covered in the video notes. Kind of want to get to the electrical performance. So what we looked at in the electrical performance was the dry and wet power frequency flashover. We only did it once for each insulator type, otherwise we would have been there for quite a while. And hopefully you noticed that the dry out distance was what determined the flashover voltage. Right, lightning and switching impulse flashover is not something we did in the practical. A lot of people confused power frequency with impulse flashover. You need to get that right. And then pollution flashover is something we did. And here are the 6 phases of pollution flashover. So you could have taken a couple of shots of the insulator flashover and seen if you could screenshots of your videos and seen if you could relate it to this. I'm sure a lot of you could see or feel the heating on the surface, and you could have put that in your reports. You could see the little dry bands occurring, dry band arcs occurring, and you could have seen the big flashover afterwards. Right. For the type B insulator flashover, pollution flashover, you could have seen that it was the hydrophobicity, and there are a couple of images where you could see the bubbles had an enhanced field and there was glowing around those bubbles rather than the pollution that the drying of the pollution layer that you saw in the ceramic type insulators. Right, that brings us to the creepage distance. The creepage distance is the length of the current path along the insulator. Right, and the unified specific creepage is the length of the creepage or leakage distance divided by the phase to earth voltage. Right, so there's different pollution levels from very light to very heavy. So you can see for a very heavy classified insulator, you have close to 54 millimeters per kV. So for example, if it's a 22 kV insulator, you would multiply 54 times 22 kV divided by √3, and that's what your specific creepage would have to be. You would design the insulator such that it is that. So it would be very long, whereas in a very light pollution, 22 millimeters per kV, same thing, 22 times 22 divided by √3, it's much shorter than the very heavy polluted one. Right. We did see some corona. You saw some arcing and some buzzing. So you definitely saw some corona. And then the voltage distribution on the insulator string is in the course notes. All right, so going back to the practical, I'll leave that table up. Right, so we'll start from beginning. Right, so here I've captured a couple of insulator details. I've got a dry arcing distance of 28 centimeters and a creepage of 73 centimeters. Right, I've got a pressure temperature of what is shown, 99 kilopascals and 22 degrees Celsius. That gives me an air density of approximately 0.98. That value you can determine on your own. And it gives me a correction factor of 0.98. So just a comment about referencing. A lot of guys went and found lots of these great references, but nobody found a reference for correcting the values to atmospheric pressure. So you've got to find the right references. It's not just about the number. All right. The capacitive divider had a ratio 4,300 to 1. It's nice to see that the WhatsApp groups are still working. I did tell some groups 4,200, I told others 4,300, told others 4,250, but most folk used 4,200. So I'm glad that the WhatsApp groups are working. Luckily, I didn't record which group I gave which value. So if we've got peak voltages, peak flashover voltages of 48 for the dry, 38 for the wet, and polluted we have 34. So our first action, let's convert that to high voltage. Right. So 48 volt peak corresponds to 206 kV. Our next step, let's convert that to RMS. Right, so we had 120, sorry, that was √3. 146 kV RMS. Right. The last step with correcting it, is you need to apply the correction voltage. So we have 143 kV, which is corrected for the atmospheric conditions. I can just copy those formulae quickly. Right, so now we've got our corrected values, and we wanted to understand what the withstand voltage is. So these are flash over values. A withstand voltage means that it does not flash over. So the withstand voltage has to be below those. Can't be above those because it's flashed over. It's broken down in air. Right. So our first step, let's go back to this table, which I asked you to look at. You've got your nominal voltage. So that's a line voltage, a line-to-line voltage, a phase-to-phase voltage, whichever you like to call it. Our maximum voltage is just a little bit above it. It just means the maximum voltage for the line. Your power frequency withstand voltage is your voltage from phase to earth. So we've got, you can see there, for the 22 kV system, we've got a withstand voltage of 50. Right, so if we've got a flashover of 143, we go and look at the closest withstand voltage below that. 3. So this is telling me it's a 66 kV. So let's start with that. So I've taken my creepage distance, I've divided it by the multiplied it by 10 to get it into millimeters, and divided it by the voltage, the phase to earth voltage. So that's 66 divided by √3, and I found the unified specific creepage distance. Go back to this table. Right, you can see there that it does not fit any of those categories. So it's the wrong voltage rating. So we need to change that. All right, let's have a look at 70 kV. That's the withstand. And 33 kV as the voltage level. Right, now you can see that the unified specific creepage distance is 31.28. And that fits within these categories. So you could have stated that that particular insulator was an insulator with a rating of 33 kV, and it would have a pollution rating of light or medium. Right, we can do the same for the others. It all looks like they fulfill the 70 kV level. So let's just right. Okay. I would have also accepted a 22 kV. 44 kV, we don't see that much of it. It might have been a bit out. All right. So that's how you're meant to determine the voltage rating. I got some great voltage ratings. I had flashover voltages of 143 and voltage ratings of 420, 150, 185. So it was very confusing to see a bit of that. All right, any questions about that? Right, so I'm assuming based on what I've given you here, I would be able to give you some flashover voltages in peak or peak to peak in the main assignment, and you'd be able to determine the voltage rating based on the tables. Is that a yes? All right, I take silence as a yes. So I'm happy that I've given you the right information and I've plugged the gap that you all had in the practical. Okay. All right, so please go through the video again. There are some details there that you need to have a look at. And you need to have a look at the voltage distribution on the insulator string that is in the course notes as well. All right, so from here, we've covered 3 of the main sections of high voltage, and the remaining section is partial discharge measurement. Right, so we'll actually not start this today, but you can start going through the course notes, and I will go through this on Monday, as well as set some sort of assignment for the last component. It'll be about partial discharge itself. All right, any queries about that? All right, great. I'm going to stop sharing and I'm going to stop it there for today. All right.